of the messages that I hope you've gotten from this meeting is that intelligence is an emergent property of complex adaptive systems, and that in some sense, every intelligent system can be viewed as a collective intelligence. This means that when trying to understand the intelligence of a system, we need to identify and come to grips with the composable diverse subsystems, which have some intelligence and agency and make it up, as well as the mechanisms that coordinate those subsystems so that their collective behavior allows the system to adapt to its circumstances, ultimately, at least implicitly, by synthesizing and executing on the fly some kind of distributed program. Of course, because the agents are themselves intelligent and the mechanisms are produced by the aggregate activity of some of these agents, those two levels adapt to one another. They co-evolve. And what I want to do this morning is tell you about two model system settings where we can talk about important elements of collective intelligence that have been missing a bit from the conversation so far: institutions and innovation or creativity. So I want to turn first to the model system of human science. We used to imagine scientists as solitary, disinterested seekers of truth, or maybe a bunch of iconoclastic geniuses. Over the 20th century, this partial provisional picture opened the door to other images, scientists as figures corrupted by social and cultural forces beyond their control. And there's, of course, truth in that perspective as well. But I want to present a way of thinking about science and scientists that draws on both the sociology of science — I am a sociologist, at least in part — and the complex systems world, a view that emerges when we turn the lens of science back on itself, a view that is very much in keeping with a lot of the view we've been talking about in this meeting, and that's to think of scientists as being more like this humble ant. Now, this ant has limited cognitive capacities and behaviors, but by interacting with other ants, with the pheromone trails they leave behind, with their collectively built environment, she and her sisters can do really marvelous things. So we shouldn't think of scientists as intrinsically special people. We're all just ordinary humans embedded in certain social and technical contexts, drawing on certain rules of interaction, equipped by certain training procedures. And because of this, scientists can build and do amazing things too. So the story I want to tell you about science is a complex socio-technical system for collective discovery and exploration, for collective knowledge making, as socially produced collective intelligence. I want to challenge the view that you often hear from scientists, which is the social parts of science are the bad parts, and if we could get rid of those icky social bits, then science would be better, and understand that actually the social parts of science are essential to how it operates. So when I refer to the social production of collective intelligence, this is what I mean: that science is an institution, a social arrangement that produces the people, the things, the interactions that allow collective knowledge to be created. Although, of course, we'll also see that the ways in which that collective knowledge creation is implemented can also lead to the creation of collective unintelligence. So by drawing on some examples from biomedicine, particularly biomedicine viewed through the lens of chemicals, molecules, and so forth, I want to draw out some of the core distributed algorithms and protocols that allow scientists in this space to become collectively intelligent, respecting the hardware, so to speak, the features of the humans that actually work together to do the science. I'm going to address one problem to try to flesh out this viewpoint, the problem of organizing attention, and point out, as I said, how the interplay between institutions and agents can also lead to some collective unintelligence getting stuck and not progressing as rapidly as one might otherwise, as well as overinvestment in certain topics. If there's time, which there might not be, I want to briefly talk about the formal analysis of scientific institutions using some game theoretic models that point out how hard it is to intelligently design institutions to produce desired outcomes. And then I'll pivot to talk about the other model system, collective creativity, in another very interesting and exciting setting, which I won't spoil So it'll be a fun surprise. Okay, so organization of attention. How do scientists figure out where they should direct their attention? Of course, they ask questions in a rich social and technical ecology, and I want to talk about a couple of papers where I've explored this question. First, this paper with James Evans and Andrei Reshetsky that was in American Sociological Review a few years ago. What affects where this representative scientist directs her research attention? Of course, her past interests, her training, but also a certain attention to her reputation in the eyes of her colleagues, her standing in the scientific field. Of course, that reputation, what we sometimes talk about in terms of her scientific capital, is the resource that in part allows her to make further research claims and have them be taken seriously. Insofar as they are taken seriously, those claims can generate a return in terms of scientific capital, which might move her up in this space of positions. Note, because of course, whenever you start talking about these things, scientists are like, wait, but I care about the truth, not, my scientific capital or my relative standing in the space of the scientific field. Note that caring about these sorts of issues is necessary even if you are purely motivated to seek the truth, because you have to stay in the game to seek the truth. So one always has to attend to these sorts of questions. And the claim I want to make is that science is leveraging and tuning and refining fundamental, whether learned or innate, human tendencies, which manifest in many different fields of collective human activity. That is, a tendency to attend to the status and position of oneself and others, as well as to the past choices of others, and that these kinds of attention can help to organize scientific attention. Now, a big distinction that one might want to make is between research moves that are herding, that kind of cluster attention, follow tradition, and moves that innovate, that strike out into new territory. Tradition and innovation is a sort of broad dichotomy. And one of the things that we found using some network scientific methods to kind of characterize tradition and innovation in a growing network of scientific knowledge is that the vast majority of moves that people make follow the herd. They contribute to tradition. They keep attention very organized. And in fact, this kind of stable attention on tradition is extremely stable over time, despite the fact that the space of possibilities explodes combinatorially as you discover new entities, as you find new ways to put them together. In fact, this herding heuristic, this tendency to sort of stick in this relatively small corner of the field, where does that come from? So we can think back to this basic position of attending to your position in the scientific field and think about a couple of different reputation mechanisms. Citations, one of the normal and easily quantifiable means that we use both as analysts and that, for better or for worse, people who are evaluating folks use as a way of kind of assessing their contribution, as well as bigger rewards up to and including things like major prizes. Now note again, caring about this sort of stuff is socially produced, right? Part of scientific training is taking someone who, say, has no idea what the American Economic Review is, a top journal in economics, and by the time you finish econ graduate school, you would be willing to sacrifice a portion of your thumb past the knuckle in order to publish in this top journal. This is actually something that these folks found in the journal Economic Inquiry. That kind of thing is a social product of participation in this scientific institution. And what we find in this ASR paper, which you'll note I did not sacrifice any part of my hand in order to publish, is that this herding heuristic is adapted to accumulating citations. That's a very valid individual goal under the current scientific institutions. It also helps to sustain organized scientific attention around a particular set of traditional topics. But that heuristic turns out to be in tension with another one involving imitating successful individuals, which is institutionally sustained by both kind of tail rewards for innovation, but also baked in by scientific pedagogy, as well as adapted to kind of longer run attention to long-lasting recognition. So what I want to underline here is that we're using basic affordances of the system hardware, in this case, human beings' tendencies to strive for recognition and status, to implement a kind of collective discovery algorithm. And as David Marr taught us, hardware affects the kind of algorithm that can be used to solve a particular computational problem. So what happens collectively as this institutionally inflected and sustained collective discovery algorithm operates over time? Does this add up to some limit in the kind of knowledge that we can produce? Well, what I want to argue is that it does in a couple of different ways. It can lead, for example, to getting stuck or needing to worry about getting stuck. This is something we studied with James, Andre, and Ian Foster, no relation, in a paper in PNAS, where once again, we have scientists operating in this biomedical space, but now they're explicitly attending to the previous choices of others in the sense that they're actually like doing a sort of preferential attachment type thing. They or at least have the ability to consider the degree, like the number of scientists who have found, or sorry, the number of links that have been found to particular chemical entities by scientists in the past. So we write down a relatively complicated generative model that gives the probability of a scientist making a particular link. You can write down some likelihood, and then given the data, we can actually figure out like what is a sort of modal strategy that would describe the evolution of this system over time. And that modal strategy is a conservative one. It's one that generally likes to connect things that are close together and basically to find some important entity and connect it to something somewhat less important. So we know that this kind of local discovery algorithm is a reasonable thing for scientists to do. Given their institutional ecology, this is a good risk-reward balance for an individual scientist. But what is its collective consequence? Is this a reasonable distributed algorithm for science as a whole? Does it impose limits on the kind of knowledge we can create? And in order to explore the collective consequences, we basically try to run the tape of history over and over again, in some cases allowing scientists to use this algorithm that we've learned from the data, but in other cases, varying that algorithm to see if we can, say, discover a network of known knowledge more or less effectively, to see if we can do better. And what we find, where on the x-axis, you basically have the proportion of the network that's discovered, and then the y-axis, a measure of sort of efficiency going from more efficient at the bottom to less efficient at the top, basically the number of experiments that you need to do in order to discover that much of the network, is that the strategy learned from the real scientific history, this Medline strategy, which is the data set that we drew on, is actually quite efficient for initial discovery, but as you unfold and try to discover more and more of the network, it becomes less and less efficient over time. And in order to figure out what's going on, we in part needed to just like visualize what this looked like. And so Andre made these very nice planar networks where we could like watch what the strategy is doing. And what it turns out that it does, as you might guess based on the kind of moves that are highly probable, is that it's very good at building up these kind of islands of knowledge, like working out the spaces around chemicals that you can connect lots and lots of things to, but it becomes inefficient when you're talking about weaving those islands of knowledge together. Now, by exploring variations in the parameters, we're able to discover strategies that would do much better, but these are risk-taking strategies. They involve doing things like combining important entities regardless of how far apart they are, or just saying pick far apart things, put those things together, those under the current institutions engage considerable risk. They involve a lot of failure, and therefore they might be challenging to get society, as the folks who ultimately sort of fund and support scientific research, to accept, because you would be getting a lot of failure by following these kinds of strategies. And so it makes sense why individual scientists certainly won't, under the existing institutions, pursue these kinds of approaches. So in some sense, I mean, I'm not saying that we're in a regime where we've reached the kind of collective ant-death spiral in science, but this is a sort of tendency that exists in current institutions. This is a limit or a failure mode of the collective discovery algorithm. But of course, we can change it because these institutions are things that are created and sustained by the activities of humans. So one institutional response might be to change how we respond to failure. Right now, when experiments don't work, when we don't find what we think we're going to find, they tend to go into the file drawer. And when you throw away a lot of knowledge of that sort, this can have unfortunate collective consequences because, among other things, you can have people doing that same unsuccessful experiment lots and lots of different times. And of course, there has been a lot of interest and attention more recently to these questions about like what happens when you incentivize certain kinds of positive findings. Those are the things that can get into the literature. Negative findings have a much harder time. So what happens if you allow this kind of coordination where people reveal both positive and negative findings and say in the limit, which is a limit that turns out to be analytically tractable in some cases, you actually just people sort of do an experiment once, reveal the finding, and then move on. And this kind of coordination can actually make even the Medline strategy quite a bit more efficient. Note that this efficiency scale is now, or is logarithmic here, so there's a big difference between a completely random strategy, a random coordinated strategy, a coordinated and uncoordinated version of the Medline strategy, and so forth. So you can actually get a lot more efficiency from this kind of coordination. And this is a basic lesson for collective intelligence, whether we're talking about human collective intelligence for artificial agents, or natural collective intelligence. It should be built for change, as Oliver Selfridge said at a meeting many, many years ago. And not just for change, but for changes in the rules for change. These kinds of limits can be broken when we change institutions. So I want to give you a second empirical case related to the organization of attention. And this is some very recent work I did with my student Bernie Koch and these colleagues, Emily Denton and Alex Hanna, who were at the time both on Google's AI ethics team. Alex is now at DARE, the distributed artificial intelligence research outfit. And this appeared in NeurIPS just this past year. And what we wanted to do is study a practice that has actually come up in this meeting as maybe something we should consider doing as a community, and that is benchmarking. Picking particular data sets, tasks on those data sets, metrics for performance, and trying to see if we can make progress on solving those particular benchmark tasks. And this was a research practice that was introduced decades ago by funders as a way of better measuring progress in AI. And this practice has some real benefits. It helps to coordinate scientists in the field around problems. It makes progress standardized and interpretable. It reduces the need for having some underlying theory of why things are working, makes peer review, in principle, easier. It allows folks to break into the space because, there's less of this elaborated apparatus of credentials and blah, blah, blah. You can just, If you're a physicist and you come up with some cool algorithm that's able to solve a benchmark and exhibit state-of-the-art or SOTA performance, then you can enter that space. And this taken together has allowed machine learning to make rapid progress, but there are downsides too. It can lead to overfitting of models to data sets, even if you do within the individual task sort of good data hygiene of trying to make sure you're not overfitting. Over time, if everyone is trying to make progress on the same benchmark data, then eventually the architectures kind of absorb information about the structure of that data set, and so you can overfit your models to data. It can also lead to folks who are participating in the research enterprise not really getting a nuanced understanding of the task. It just turns the real world problem into this very abstracted game that you don't really need to know very much about. It's just fundamentally a bunch of, data in some structure that you're trying to do some task on, and you can get away with not really understanding it very well. It can lead to particularly risky outcomes where the benchmark and the real-world data generating process get out of alignment. And so there are, for example, very prominent failure modes in this direction, like with facial recognition data, where those benchmark data sets used in that space are not at all representative of real-world faces, and so they're much better at recognizing white faces, for example, or lighter-skinned faces. There are particular configurations of individual characteristics, like darker-skinned women's faces that they're very bad at, et cetera. And so these things can distort scientific progress. They can create unintended social harm. They can waste time and money. So to study this question of how attention was distributed across these data sets, we used something called Papers with Code, a repository of papers, benchmarks, and the code associated with them, an ontology of tasks created by the research community, crowdsourced and algorithmic task and data annotations, did a bunch of data cleaning, and then asked the question, well, how is this attention distributed? So consider someone trying to decide what benchmark to use. This is not a very good picture, so let's say, okay, here's someone trying to decide what benchmark to use. If you think through the cost-benefit calculus that this person experiences, there's strong pressures to use popular benchmarks rather than ones that might be closer to the real-world task you're trying to study, or creating your own. It's just easier to say, well, this really well-studied, well-established, and existing benchmark data set is good enough for this task, so I'm going to apply my algorithm to this and say, look, I have state-of-the-art performance on, whatever. So we wanted to ask 3 questions. How concentrated is benchmark usage? Where do the benchmarks come from? And what organizations are creating widely used benchmarks? And in the interest of time, I'm going to blast through this. What we find is that tasks have become concentrated on fewer data sets over time, measured by Gini, what we often use to measure wealth inequality. This is true except in natural language processing for reasons having to do with the structure of that field. And across machine learning research and in many different domains, the Gini is above 0.7. So if you're familiar with looking at what is considered a outrageous level of wealth inequality in a country, this is very, very unequal. There are some data sets that get a huge amount of attention and lots of data sets that get almost nothing. Do researchers create unique data sets? Yes, they actually create more data sets in a particular domain than they import from outside, but when it comes to actually using data sets in papers, they mostly use imported data sets, again, except in NLP. In this case, we find no significant evidence for time trends. And then the kind of, in some sense, easiest to state and most disturbing finding is that over the 6 years that we studied, more than 50% of the usages come from data sets produced by 12 organizations. And these are a mixture of academic institutions and companies, mostly in the West, mostly, or I mean, in fact, all very elite. So this huge amount of research attention is focused on data sets that in some sense are reflective of a very narrow set of institutions, institutional interests. So the takeaways here, right, are that researchers in machine learning are using fewer and fewer benchmarks across the field. They're creating task-specific benchmarks, but generally not using them, and that a handful of elite institutions are creating the benchmarks that actually get used. So in the context of the broader point I want to make about how science as an institution operates, you can see here once again how individually reasonable behavior is leading to collective behavior that may be substantially distorting scientific progress, as well as, in this case, producing real and significant real-world harms on particular groups. So what I want to do, I'm going to skip the game theory. If you want to talk game theory, we can do that later. And in the remaining 5 minutes, we have a little time for questions. I'm going to talk about another important example, and that is collective creativity. And I want to talk about understanding collective creativity through the lens of evolution, viewing evolution as a form of inference, as lots of folks have taught us to do, where we underline that evolution is in some sense a special kind of computation, one that's implemented in settings where you have some population that exhibits variation, inheritance, and differential survival. And what I want to argue is that evolution provides us with a way of understanding sociocultural change and collective creativity. In this case, in the domain of culture, where by culture, I just mean a shared regularity in the organization of experience or the generation of action that's acquired through social life. So if you want to read, I'm going to go really fast here. So if you want to read more about it, there's this paper with my student Bernie and Daniele Silvestro, Evolutionary Dynamics of Cultural Change. The basic furniture of the theory that we develop comes in three types: the personal culture that's in people's heads, the cultural things that are in artifacts out there in the world, and the cultural forms that are in some sense kind of categories of cultural things. And at the end of the day, cultural change is really just about changes in the distribution of personal and public culture over time. Public culture is easier to work with because you don't have to ask people questions. You can just sort of see what's out there in the world. So the case I'm going to tell you about is metal music. Okay. So why study this? My student is substantively, I mean, I like some metal music, but apparently I have very basic taste in this space. It's also interesting because it's not reducible to simple economics. It's also not like problem solving. This is an example where people are really creating under sort of autonomous, self-imposed constraints and interests. And we have very complete data coming from this data set called the Encyclopedia Metallum, which is a Wikipedia-like resource that's actually been existing for almost as long as Wikipedia, and maybe longer, actually. And the basic thing we want to try to understand are birth rates and death rates, where birth rates are the rates at which metal bands make new metal bands, and death rate are basically the rates at which they disappear. What we want to try to understand in this space are which evolutionary mechanisms can drive variation in birth and death rate, things like mass extinctions, things like competitions between different bands or genres for some kind of cognitive niche, key innovations. These are moves that in some sense create more space so more entities can exist, or some kind of exogenous forcing like through some economic driver. So yeah, sorry, thank you. I will finish up, so there's time for like a couple of questions. Okay, thank you. So in the metal context, you know, this would be like grunge music wiped out or allegedly affected the metal space, et cetera, et cetera. So the long and short of this is that using these elaborate Bayesian models of birth-death processes, we can say, like, okay, if the dotted line shows the dynamics of birth and death rates in the real data, and the solid lines show what we're able to infer by trying to fit these models to the data, what might explain what's going on? And so competition does a very bad job of capturing the full dynamics. If, however, we look at models where we allow innovation to occur, in other words, where we allow the niche to expand as a function of, in this case, well, I'll tell you in a second what drives the niche to expand, but the underlying idea is something is happening that makes more space available to this particular evolving population. That actually captures a lot of the dynamics of the data. And the inferred niche expansion basically looks like this kind of sigmoidal thing. We actually have been able to explain that expansion of the niche by looking at the creation of new genres. So basically, as folks in this cultural population invent new forms of metal music, we can actually closely ratchet that expansion in new genres to the overall expansion of that niche. And this turns out to do an amazing job of explaining what has gone on here. So just to wrap up, what I want to emphasize is the importance of keeping creativity at the center of thinking about collective intelligence. I like this metal example because it's a kind of open-ended or aimless activity. It's not problem solving. And I think that's an important part of the story. So I hope by considering these two model systems, you've been inspired to think a little bit more about the importance of innovation, our institutions, and creativity in our understanding of collective intelligence, not just when it comes to humans, but other groups as well. I want to thank the folks who have funded the work. Thank you for your attention. Thank you to Harlan for reminding me to keep on time, ish, and not at all. I have time, I think, for like one question.